let's get started. This is our goal today. We're going to be working on essentially number one is how to make simple sketches of derivative functions. We have done this. We're going to look at 4 situations. After that, hopefully we'll have time to do multiple derivatives. And then lastly, I'm going to show you a shortcut method for finding derivatives of simple radicals. So kind of overlap here, but overlaps are good. Suppose you want to do a polynomial. First thing you do is identify, in this case, 3 different locations where the hills and valleys are, because at these 3 points, the derivative is guaranteed to be 0 because it's horizontal. Right? Horizontal tangent lines have 0 derivatives. And then you do these little dotted lines. These dotted lines are not really physically there. They just help in the construction. And this one happens to be on the y-axis, so it's going to go down there. And this one goes over here. So what's really important is that I now know, overkill, that the curve passes here, passes through here, passes through here. I also get as an added bonus that there's region 1. There's a little guy up there. So from here to the axis is 2, from the axis to here is 3, and from here to the end is 4. So that means I now have 4 regions. So when you do polynomials, find the tops of hills and valleys. They make zeros happen. Break your region into, in this case, 4 separate regions using these construction lines to help you do that. And then for each one of them, we'll start with region 1. Find out if the curve has a positive tangent line or a negative. So if I chose any point on this curve, would you agree it's positive, it's sloping upwards? So in region 1, positive, right, the y here represents the value of the derivative. Positive is above. So that means you shade here, above. Would you agree in region 2, all the tangent lines are pointing downwards? Right, that's a negative slope. In region 3, positive. Region 4, negative. And what you now have to do is kind of put all the information together with a simple curve, you know, the simplest curve that does everything you need. And I would suggest that the curve goes down here, and it has to loop round to here, and then it has to loop round and finish like that. And I've now done a pretty reasonable sketch of what the derivative of this curve would look like. Kind of did something a little bit simpler than that last time. We're comfortable with how you deal with polynomials, right? Okay. Now, we have done vertical asymptotes, and I will come back to that, but I want to put a new guy in town that we haven't done. And that is, how do you do sketches of functions that are made up from straight lines? So what we're talking about here is not one straight line, but a function that's got a number of straight lines. So it goes up, and it goes maybe straight, and it goes down, and it goes straight, and then it goes down. So I'm talking about functions that are made up of a number of straight lines joined together, like here. Now, if you want to draw what the derivative of this function looks like, you have to approach it in a different way. What we look for in shapes like this is not where the hills and valleys are, and that gives us 0 derivatives. That's not much use for this kind of shape. What you look for instead, well, anybody tell me what you think I'm going to use instead, before I do tell you. I need a way of splitting this shape into manageable chunks so I can find the shape of the derivative for. So where do you think
Is it where the
I'm going
line
to
is
use?
horizontal?
No, but I understand that. No, not directly at least. Last chance. Okay, going to use the corners. When you get a straight line function, right, a function that's made up of straight lines joined together, as we have here, and there's a lot of them, the corners are the key places where things change. So this is going to be region 1. This whole chunk in here is region 2. I guess I'll need to make these a bit higher so that they're all in the same place. There's my region, my 3rd. There's my 4th, and there's my 5th. So got region 1, region 2, region 3, region 4, finally region 5. Now things get a little bit different here. Let's take this piece here, right? The graph in region 1. Every single point on this graph, because it's a straight line, won't its tangent line be the same number? In fact, won't the tangent line be on top of the graph? It's a funny kind of thing to talk about as a tangent line, but would you agree that the slope here, right, whatever that slope is, it's positive? And would you agree that if I found the slope at this point, it would be the same slope at that point, it would be the same slope at that point? Now, what does that mean then? Well, would you agree it's positive? Right. So it's positive. But it's also the same value. So I'll draw a line like that. Now, what about region 2? Would you agree that if you found the slope of this line, wouldn't the slope be 0? Right, horizontal line, 0. So that would be, and the only reason I'm making this a bit thicker is because the x-axis is in the way. So it's not that thick. It's just trying to make it emphasize it. Right, now we have a problem. What happens at the corner? Well, what happens at the corner is a little open circle. Why have I put an open circle there, which means you cannot use me? Why haven't I filled one or both of them in with a dot? What's the reasoning? What's the problem at the corner that has made me do this?
There's no possible tangent to that point.
Right.
Is there?
I mean, what's the tangent at a corner, right? It's a corner, right? Don't you have to have a kind of smoothness? So, rule of the game. If you see a shape made up of straight lines, the point where the corners are always going to be open dots. Okay. Region 3. Let's speed this up a bit. What do you notice about every point on region 3? Isn't it the same number but downwards? So it's the same negative number. That's going to be that guy. What do you know about region 4? Isn't that a horizontal line? Or at least I try to draw one. And what do you know about a horizontal line is it's got 0, right? It's 0 slope. And the last one, region 5. In this case, isn't this guy, this slope, the same number? And isn't it a negative number, right? Sloping down. So the derivative of this straight line curve is basically a whole load of horizontal lines like a piecewise curve. Would you agree that's maybe not what you thought the derivative was going to look like? There is a temptation, don't do it because it's wrong, for people just to join these together with little vertical lines because it feels like they should have them. It doesn't. They are separate, right? They don't connect. Are we okay with straight lines and how you do them? Right? You're going to get a whole sequence of horizontal lines, some plus above the axis, some negative below, but everyone is going to be separated with these little open circles. because you can't get derivatives at corners. I'm ready to move on to the next one if we're good. Okay. Third one in the list, we've seen one before, so this is a second one. Do a little bit more complicated this time. So we're going to look at how do you find the derivative of a function that has vertical asymptotes. Well, I'm going to do a vertical asymptote over here. And I'm just going to call it -3, just so I've got a number to point at, right? And I've got another one here at x equals 4. You don't need to be told these numbers to draw the sketch. I'm just putting them there to make it easier for me to talk about them. And what will we have? I think we're going to have a vertical guy that looks like this. There. So what have I got? A volcano at x equals -3, and I've got a 1 of each at x equals 4. It's a pretty typical looking vertical asymptote. Isn't that the kind of thing you get with a rational function? Not that unusual, you could see that. So now we have to figure out how to sketch its derivative. In each situation, you have to kind of adapt to the information. So how do you adapt to vertical asymptotes? Well, the way I'm going to split this shape up is a little bit of this and a little bit of that. So what's that? The vertical asymptotes are useful for splitting the shape up. Also, if the shape has it, because it might not, but in this case it does, would you agree at that point there is a 0 slope, right? A tangent line that's 0. And that, and I'm going to change the color just for cosmetic purposes, gives me a 0. So this shape is going to be split into region 1, which is this guy. Region 2 is from here to here. Region 3 is from here to here. And region 4 is that piece. So I've got region 1, region 2, region 3, and lastly region 4. And I'm going to do a little bit of what we did in the first case. This piece of the curve here, would you agree that all the tangent lines are positive, right? So shade that. In region 2, would you agree from here to here, isn't the curve's tangents always negative? So I'm going to shade here. In region 3, positive or negative? What do you get here?
Positive.
Great. And what do you get? And be careful. What do you get in the fourth one?
Positive.
Yes. I don't know why, but some people find that weird looking, but it isn't. That's what you get. Now, what people might do next is, and it is wrong, they might think, well, when I had polynomials, I kind of went from here to here and then here to here, and I'm not quite sure what to do there. But they just try and join the regions together. And if it's polynomials, that's exactly how you would do this, right? You just start this region and try to get to that region. The reason it doesn't work here is because these vertical lines, these vertical asymptotes do something different. For starters, The curve doesn't pass through where my finger is. So let's look at this guy here in region 1 in a little bit more detail. If I choose this point, can you imagine the tangent line might be 2, right? Slope of 2. As I get a little bit nearer, couldn't the tangent line be positive 10? What happens is to the curve, as you get nearer and nearer, doesn't the tangent line go vertical on you? Can you imagine very close to that? Wouldn't the curve be virtually vertical? And isn't virtually vertical virtually infinite? So what that is telling me is that for this piece of the curve, as you get closer to the line x equals -3, you get a vertical asymptote. So vertical asymptotes generate derivatives with vertical asymptotes at the same place. Right, let's look at region 2 here. What happens as I get closer and closer to -3? Well, doesn't the tangent line start off with maybe a slopey -5 and then a -10 and then vertical, but negative vertical? So it's coming down the way. So vertical tangent lines in the original function generate vertical asymptotes in the derivative, but they're not the same shape. This is a volcano and this is a 1 of h. Now, let's look at this guy. Vertical asymptote. Vertical asymptotes generate vertical asymptotes. Can you see in this case, both are positive? Can you imagine? 10, 20, 50, a million. What about on this side? 10, 20, 50, a million, still positive. A volcano. Now, this guy and this guy have to come together. So how about just doing that? So we fix that issue. And then you should be quite pleased with yourself and you'll say, hey, I'm done. Not quite. Have you noticed that as you travel this direction to the left, don't the slopes get smaller and smaller and smaller? And doesn't that mean then, and I wish I'd give myself more room, that essentially means that this guy flatlines on the sides. That makes sense. At the edges, the curve's tangent line are almost 0. And as you get closer to the end, it gets more and more 0. So essentially, it's a horizontal asymptote. So horizontal asymptotes generate horizontal asymptotes. Vertical asymptotes generate vertical asymptotes, but not necessarily the same shape. I'm getting a lot of nods in that. That is good. I like nods. Nods normally mean that makes sense to me. I can see why that's happening. Okay, we have got one last one to do, which has definitely got a weird name because I couldn't think of a good one for it. And I'm calling it the rest. Non-vertical asymptotes. What on earth am I talking about when I use that term? Well, it's probably not the best term, but as I said, it's the only one I can think of. There are some special curves. Let's talk about one of them, the half circle. And can we, these numbers are just for reference, just to give you an idea. Here is going to be my original function. Here is going to be the sketch of my derivative. Now, when you look at a simple shape like half a circle, you're going to, I think anyway, you're going to be surprised by how complicated the answer is. Well, I know it might not look right. Can you pretend that that's the top of the hill? I think I kind of did it, right? And would you agree that at that point the derivative is 0? So not doing anything special. The y-axis is in the way, but I can still do that. There we go. And that breaks the region into 2 pieces. And on this side, would you agree that all the derivatives, all the tangent lines are positive? And on region 2, would you agree that they're all negative, right? There is nothing too weird happening yet. So you might think, well, that's it. I can't really see any more information. I might be tempted just to draw a straight line because that's the simplest shape that you could imagine. And I could understand you want to do that, but it's not correct. And it's not obvious, and hopefully this will make it more obvious. If I draw a complete circle, and we look at the end point right at 4, do you see that the tangent line is actually a vertical line at the end? See that curving down? And at this side here, would you agree that it is here and here? Isn't it vertical? So I'm going to draw these down at x equals 4. I'm going to draw this fella down at x equals -4. And if it is a vertical tangent line, doesn't vertical tangent line transfer into vertical asymptote as a graph? So what happens as you get closer and closer and closer to 4, you get -10, -20, -20 billion, negative infinity. It goes vertical asymptote on you, because at that point, the derivative is vertical and negative infinity. On this side, you get positive, and then you just do this. That's a lot weirder than I think you would have expected from half a circle, right? Do you agree its derivative is quite weird looking? That's it. Now there's 2 versions. That's one special case of the rest. The thing that kind of makes these the same is that they have vertical tangent lines in them. This one had 2 vertical tangent lines at the end. The second one that I'm about to draw, and I'll give you an example of it. The cube root of x is like this. Now, if you focus at the origin, right there, the cube root function has a vertical tangent line. It curves in vertical right at 0. Right? It doesn't come in at an angle, which if you draw it, you might do that, but it actually comes in vertical. That is going to cause the same problem that this fella caused. Here, there's going to be a vertical tangent line. On this side, everybody is positive, and anything on this side, everybody is positive. But as you get closer and closer, it's +10, +20, +1,000,000. You get a vertical asymptote. And on this side, you get a vertical asymptote. So something like the cube root of x has a vertical asymptote. I guess I could make the curve go a little bit further, something like that. Would you have thought of would you have thought that something like the cube root of x would touch such a weird looking derivative, especially at 0? Okay, that is the end of how to find graphs of tangent lines, or graphs of fault derivatives, I guess I should call them. Any questions before we move on to the next bit, which, by the way, is going to be pretty easy. Okay. Let's do multiple derivatives. Let's do 10x cubed, 2x squared, plus 7x minus 11. Right, there's my function. Oh, by the way, we're going to use the shortcut method, so life should be easy. When I write that down, it has a name. I don't know if I've ever mentioned it. I'm now mentioning it. It's called the first derivative. And basically, the power rule, right? Multiply by the power, reduce it by 1. So you get 30x squared. Multiply by the power, reduce it by 1. What does 7x get you when you use the shortcut method for derivatives? What does this plus 7x get you?
7.
Right. What does the minus 11 get you?
0.
0. Are we comfortable with the, I kind of call them special situations, right? Special cases, right? 7x gets you 7, minus 11 gets you nothing. Now, have you noticed that I'm not using the f dashed of a thing? Do you notice that we're calling the thing x all the way through? Which is much, much more simpler to, focus on it, because that's really what we're doing, right? Now, multiple derivatives says this. Can't I use this as my starting point? Then shouldn't I be able to differentiate this guy? And if I differentiate him, I call him f double dashed of x, and it has a not surprising name. It's called the second derivative. So how do I find the second derivative? I differentiate the first derivative. So here goes, multiply by the power, reduce the power by 1. Now, if I can do that, why should I bother stopping? Couldn't I just do it again? And if I differentiate it a third time, we use that, and it's called the third derivative, and we get that. Can I keep going? Pretty straightforward. I want to show you notation issues. You know the next derivative is going to be called the fourth derivative. How do you think I'm going to write the 4?
I believe it's a 4 in brackets.
Oh, very interesting. Yes, it is. How else? And that's correct. How else could I write it?
Roman numerals?
Yes. So you can write it like that. Or just like you said, Sabrina, you can write it like that. What you don't write it like is that. Now you might say, what's wrong with that notation? You did it the first 3 times, why can't I keep doing it? The reason why that notation never gets used is, how many derivatives is that? You agree that that notation's not good, right? So don't use it, right? Now, you could keep going with Roman numerals, 5th, 6th, and 7th, but the Roman numerals also eventually get kicked out. We very typically use these for the first 2, 3, 4 derivatives. They're quite convenient and they're nice, and we like them. The number thing, tends to get used when the derivative that you're doing is quite high. See, if I went and said to you, that derivative, I would be saying you're finding, and I can't think of any reason in the universe I'd ever want to, but aren't I finding the 103rd derivative? Right, that would take a while. Agreed? But you can tell it's the 103rd derivative. Unless you are really good at Roman numerals, do you really know what derivative I've just picked?
The 17.
17.
57.
Okay, you are really good at Roman numerals. Can you imagine I could be doing MCX, V, D, D, I, and really screw up your life? Can you see that the Roman numerals are not really designed for more, probably, what, about 6 or 7, and then it starts getting clunky. So yeah, we tend to use Romans for the early ones and then numbers when they get messy. And that's just the notation issue. But are we happy with, you can do multiple derivatives by just doing what you always did, but using the previous answer to keep going? Here's an interesting fact. Do you know if you start with any polynomial, won't you eventually get to 0 if you keep taking derivatives? Think of it. If you start with a cube, don't you get a square, and then you get a linear, then you get a number, then you get nothing? If I started with x to the 10, wouldn't I get x to the 9s, 8s, 7s, all the way? Eventually, I'd run out numbers. That's true for every polynomial. While we're talking about notation, let me show you another notation issue. Sometimes functions are written as f of x equals x cubed. Sometimes functions are written as y equals x cubed. We all should be happy that they are mathematically exactly the same information, right? They mean the same thing. Now, when you write it this way, the derivative uses the f dash notation, and that's the only notation I've been using so far. But when you have functions written this way, that means the same as that. So this is the dy by dx notation. It means the derivative. Honestly, I can't remember who it is. It could be Leibniz who did this notation, or it could have been Newton, because Leibniz and Newton are the, the guy with the gravity and the apple hitting you in the head, Newton, right? Leibniz is a German mathematician. One of them came up with this notation, and it is kind of helpful, because if you write y equals, how do you tell someone you've done the derivative? Well, just to show you, there is another notation that you might see in some textbooks. Does y dash kind of make sense to you, what they're telling you you've just done? So f dashed of x means first derivative, y dashed would mean first derivative, and dy by dx would mean first derivative. And if you're wondering why we even bother with that middle one, because that one seems much more natural and it seems to fit this notation, right? Is that we're going to be doing other things in the future called differentials. And you're going to be doing Calc 2, hopefully. And in Calc 2, sometimes you'll find that this notation, especially the way it's written, is very helpful for doing certain manipulation processes. So I want us to get comfortable with this notation, because it will, in the future, maybe not right now, seem like of any great benefit, but it's a good notation for other reasons. Are we cool with multiple derivatives?
If you were using, can you use the dy over dx notation for multiple derivatives? How would you write that?
For multiple derivatives, yes, very clunky, but I'll show you a third derivative. Now, do you notice I put the 3 in 2 different places, which seems wrong? There is a good reason for it that I can't go into right now, because you don't know the math that you need to know to be able to make sense of why that's a notation. Thankfully, we very, very rarely ever use that notation. We use the dy by dx a lot, but that's not as helpful. But it gets, you know, there's reasons behind it. I could tell you, right? If you take dy by dx and you differentiate it, what you're doing is you're doing this. You're differentiating this with respect to x. And the d's go together, and that gets you the d squared, and the dx's go together. Technically, you should write that. But you know, mathematicians don't like brackets, so they write that. I don't know that probably helps you now that I've done that, but that's the reasoning behind the clunky notation. But let's do the last thing then. If don't let the notation get in the way of the process. Would you agree you just keep differentiating until, you know, you're told to stop? So who's left? The last guy in town is derivatives of simple radicals. And we're going to use the shortcut method. We're going to find a shortcut method. Right, let's start by what do I mean by a simple radical? A simple radical would be the cube root of x. A simple radical would be 4 square root of x. A simple radical would be 1/2 the cube root of x to the 4. All of them count as simple radicals. What makes them simple? The guy inside the radical is x or a power of x, right? It's x squared, x cubed. These are what I mean when I say simple radicals. This is what I mean when I talk about complex radicals. So it'll be the cube root of x add 1. It won't just be the square root of 4x, right, as it is here, but it might be 4x minus 1. And it won't be 1/2 of x to the 4. It'll be 1/2 of x to the 4 plus 2x plus 1 plus stuff. So complex radicals have more than just x inside or powers of x, right? They have 2x's of x's plus 1s. They have stuff that isn't just x or x squared, right? You're allowed x squared. That's okay. So let's look at finding a derivative of a cube root function, right? A nice simple radical. I'm going to write down in English the shortcut method called the power rule. And it in English is multiply by the power and then reduce the power by 1. In fact, that's pretty much what I say, isn't it? If you kind of play this video back, you'll hear me say multiply by the power and reduce the power by 1, right? I keep saying that. It helps to reinforce the rule. So you're the first mathematician to deal with the problem. I want to find the derivative of the cube root of x, and I do not want to do it as that h tends to 0 because it would take me forever, and I don't want to do it that way anymore. I want a shortcut. And we want to see how we might be able to do it. The first thing they would do would be to realize that can't all radicals be written as fractional powers of x? So a cube root would be a third power. And that's a big clue to how this is going to work. Let's use that notation. How do you find the derivative of x to the power of a third? What do you think might be the trick?
Would it just be 1/3 x?
I like your start. Yes. Anything else?
So we're still subtracting a whole 1, correct? So
Correct.
that would be -2/3, power -2/3.
You nailed it. Together, you made a partnership there, right? Haven't I actually just done the power rule? I've just done it with fractions, right? I've multiplied by the power, third, and I've reduced the power by 1. Now, if you take a third and you subtract one whole amount from it, you do get -2/3, right? So you've got to be aware that, you know, there's fractions involved in taking things away. Now, this is the correct answer, but it is not considered good form. Right? I call it style points. This guy needs to look pretty. And there are 3 rules for style points in every situation, but only one of them applies here. The first rule of style points is collect like terms. Well, that's not an issue, that's not happening here. So collect like terms. The second rule is factor the heck out of it, which isn't an issue either. And the third rule is the one we're going to use, and that is make it look like the original. Wasn't the original a radical, right? This question was a radical. This guy needs to look like this guy. So what we're about to do now is not calculus. We are about to do algebra from Math 99. So we're getting the cobwebs out. Here goes. Are you happy about a negative power being written as a positive power on the bottom? Are you happy with that rule? Do you remember doing it way back in the day? Okay, next rule. Can't you turn fractional powers into radicals? I mean, here didn't I take a radical and make it a fraction, but couldn't I take a fraction and rewrite it back as a radical, right? It works both ways. So this guy is going to get turned into a radical and we're finished. What radical is x to the 2/3?
Root of x squared.
Nailed it. Agreed. Do you notice that the denominator?
What happened to the negative?
Yeah, what negative?
Negative.
Oh, the negative here?
Yeah.
It became positive 2/3 because I moved it from the from where it is on the top essentially to below from the numerator to the denominator.
But why would that change?
I could. Well, there's a rule in math that says x to the -3 can be written as 1 over x cubed. Right. If I rewrite this guy, slightly different form, it might look a bit clearer. Would you agree that guy and that guy are the same guy? Right? That this and this are the, oops. That this and this are the same guy, right? And can't you move negative powers downstairs?
Yeah, never mind.
That's what I'm doing. So the negative get converted to this. And then this get converted to a radical and we're finished. That makes, are we good now? Okay, let's try another one. I know, probably don't have time, but let's get one more done before we call it good. So how about square root of x to the 7? So I'm picking this one because it's a little bit different than the other one. In fact, let's put in a 4 there just to make it more interesting. So first thing you would do is convert it to a fractional power. So the square of x to the 7 is 7/2. Hopefully you remember that. Now, derivative. Oh, let's use this notation just to be different. Multiply by the power and reduce the power by 1. 4 times this guy gets you 14 eventually. And if you reduce the power by 1, you now only have 5/2. So do you see in this question, you didn't end up with a negative power of x, right? It's still positive, just a little bit less positive. Style points in this case then only requires one fix. Don't I have to convert this guy into a radical and 5 halves, square root because of the halves, and 5, and that is considered, oops, the correct answer. In other words, that's the best form that you can write that answer. Are we good? I'm going to call it a day then. Say hi and bye-bye. Of course, officer is about to start, so if you want to ask me questions, I'll see you there. Michael, you got a question? Michelle, I should say, sorry. We're good? Okay.